BGP is often introduced as the routing protocol of the Internet. That is true, but incomplete. It is also the policy engine beneath modern data center overlays. In the next 30 minutes, we will build one practical model, from eBGP and IBGP through route selection, route reflection, multi-protocol BGP, and the evidence needed to trust the forwarding result. The core learning is simple. BGP exchanges reachability claims under policy. A session is only the beginning of the proof. Here is the agenda. First, we establish what BGP carries and how a session becomes operational. Second, we separate EEBGP, which crosses an autonomous system policy boundary, from IBGP, which distributes selected reachability inside that system. Third, we dissect and update and follow a route through policy, path attributes, selection, and next hop recursion. Fourth, we scale IBGP with route reflection and extend the session with multi-protocol capabilities. Fifth, we apply a minimum safe policy and security posture. Finally, we prove the result from neighbor state to packet evidence. The core learning is not a mnemonic. It is the dependency chain that makes a BGP route useful. A BGP route combines destinations with path attributes. In classic IP version 4 unicast, the destination is a prefix in the network layer reachability information field. The attributes describe the offered path. For example, where it came from, which autonomous systems it crossed, what next hop to use, and how local policy should treat it. Import policy decides whether the offer enters the local decision process. Export policy decides what leaves for each peer. That makes BGP a policy-controlled database exchange, not a physical topology discovery protocol. It can advertise a route that is later rejected, lose one that was once selected, or carry EEVPN objects that never become usable forwarding state. An autonomous system is a set of routers operated under a common routing policy and identified by an autonomous system number. EEBGP crosses between autonomous systems. IBGP distributes BGP reachability within one autonomous system. The distinction is about the policy boundary, not merely whether two routers are physically adjacent. An EBGP session may use directly connected interfaces or loopbacks reached across several hops. An IBGP session may connect neighboring routers or distant route reflectors. The enduring model is this. EBGP imports and exports claims across administrative boundaries. IBGP carries the resulting policy decisions across the internal network. The IGP still supplies internal reachability to session endpoints and next hops. BGP uses TCP, normally Destination Port 179. TCP provides reliable ordered delivery, so BGP can focus on routing state rather than retransmitting individual protocol messages. Before BGP can negotiate, the chosen source and destination addresses must be reachable. Transport filters must permit the connection, and both sides must agree on the peer identity and autonomous system numbers. Direct eBGP commonly uses connected interface addresses. Designs using loopbacks gain stable endpoints, but require explicit update source, multi-hop reachability, and a route to the remote loopback. IBGP commonly uses loopbacks for resilience. When a neighbor remains active, test this lower transport path before debugging route policy. The BGP finite state machine moves through idle, connect, active, open sent, open confirm, and established. Active is not healthy forwarding. It means the speaker is trying to acquire a TCP connection. After TCP connects, each side sends an open. If the version, autonomous system identity, hold time, BGP identifier, and optional capabilities are acceptable, keep alive messages confirm the session. Only then does the state become established and normal update exchange begin. A notification reports a protocol error and normally closes the session. This sequence gives a diagnostic map. Connect or active points downward to reachability and TCP. Open sent points to peer parameters. Established permits route investigation, but proves no useful route by itself. The open message establishes who is speaking and which extensions are available. Its base fields include the BGP version, the sender's autonomous system value, hold time, BGP identifier, and optional parameters. The capabilities mechanism inside those parameters lets peers advertise support for features such as multi-protocol address families, route refresh, 4-octet autonomous system numbers, and add path. A capability advertised by only one side is not a bilateral contract. For MPBGP, both peers must advertise the relevant address family and subsequent address family pair. Therefore, a base session may be established while EEVPEN is not negotiated. Always inspect negotiated capabilities per peer and per address family, rather than inferring them from the green session state. An update message can withdraw destinations, advertise destinations, or do both. In the base IP version 4 format, it begins with withdrawn routes length and withdrawn prefixes, continues with total path attribute length and the attributes, then ends with advertised network layer reachability information. An advertised destination inherits the attributes carried in that update. A withdrawal says the previously advertised path is no longer available. It does not need the old attributes repeated. MPBGP moves reachability into MP reach, NL, RI, and MP unreach, NL, RI attributes, so one session can carry other families. Operationally, read an update as a state transition. Remove these candidates, then add or replace these candidates with this attribute set. Our FC4271 gives us a durable conceptual pipeline. AGI-RIB contains routes received from a peer before the local decision. Import policy may reject them or assign local preference and other internal treatment. The decision process chooses eligible paths for the local RIB. Export policy then determines the ADJ RIB out for each peer. An implementation need not store 3 literal tables with those names, but the states remain distinct. A route can be received and rejected, accepted but not selected, selected but not exported, or exported and later withdrawn. Never say merely that BGP has the route. Name whether it was received, admitted, selected, installed, or advertised, and cite the command that proves that stage. eBGP connects independent policy domains. Each side should define what it expects to receive, what it is willing to advertise, how much route state is acceptable, and which attributes may cross. Classic EEBGP usually adds the local autonomous system number to AYS path on export and, for directly connected sessions, uses a short time to live. Many implementations also change the next hop when advertising externally. Those defaults are useful, but they are not the contract. The contract is explicit policy. Customer prefixes are not the same as a default route from a provider, and a peer must not accidentally turn your network into transit. Treat every eBGP edge as untrusted input and constrained output, including private data center interconnects. A BGP speaker originates reachability only through an explicit mechanism. A common network statement matches a prefix already present in the local routing table. It does not create reachability by itself. Redistribution can inject routes from another source, but it must be bounded because it can import far more state than intended. Aggregation can advertise a less specific prefix, provided the design preserves correct reachability and withdrawal behavior. After origination, export policy still decides which peer receives the route and with which attributes. If the supporting route disappears, the BGP advertisement must be withdrawn. The safe proof chain is: supporting route exists, origination rule matches, BGP selects the route, export policy permits it, and the peer confirms receipt. AS path is a well-known mandatory attribute that records the autonomous system sequence an advertisement has traversed. When an EEBGP speaker exports a route, it normally prepends its own autonomous system number. If a receiving speaker finds its own number in the path, the route is rejected as a loop. The path also becomes a policy signal. A shorter path is commonly preferred after stronger local policy, and deliberate prepending can make one advertisement less attractive to remote networks. But ISS path is not a physical hop count and is not a security proof. Policies, confederation segments, aggregation, and malicious or erroneous announcements can change what it communicates. Use it for loop prevention and controlled policy, then apply independent validation. BGP policy becomes clearer when relationships are named. A customer pays for connectivity and generally receives routes the provider is authorized to carry. The provider may advertise that customers' routes onward. A provider supplies upstream reachability, often a default route or a broad table, but should not receive routes that would make the customer unintended transit. A settlement-free peer normally exchanges customer reachability, not routes learned from other peers or providers. These are economic conventions, not fields in the BGP header, so policy must encode them. A useful design test asks for every learned route. From which relationship did it arrive? Which destinations may use it? And to which relationships may it be exported? A multi-homed autonomous system has more than one external path, but inbound and outbound traffic are controlled differently. Outbound choice is local. Policy can set weight on some platforms, local preference across IBGP, or allow later tiebreakers such as AISS path and IGP cost to decide. Inbound choice belongs to remote autonomous systems. You can influence it with selective advertisements, more specific prefixes, autonomous system path prepending, MED in the right relationship, or provider-defined communities. You cannot command it. Remote policy may override every hint. Therefore, define the failure goal first. Active use, simple backup, customer-specific exit, or deterministic failover. Then measure both directions, because a beautiful outbound rib says nothing about the return path. Core attributes are easier to reason about when their owner and scope are explicit. Local preference expresses preference inside one autonomous system. Higher is preferred, and it is normally carried to IBGP peers, not EBGP neighbors. AS path travels between autonomous systems and supports loop prevention and policy. MED suggests a preferred entry point to a neighboring autonomous system. Lower is commonly preferred, but comparison rules and propagation are implementation and policy sensitive. Next hop identifies the forwarding recursion target and must resolve. Communities attach reusable policy labels. Their effect exists only where policy interprets them. Vendor weight is local to one router and is not a BGP standard attribute. Before changing an attribute, ask who sets it, who receives it, and who can override it. Best path selection starts before the famous tiebreakers. Import policy first decides which candidates are eligible and assigns local preference. The next hop must be resolvable. The implementation then compares eligible paths using its documented order. In EFRR routing, that order includes weight, local preference, locally originated status, autonomous system path length, origin, MED under defined comparison conditions, EEBGP over IBGP, IGP cost to the next hop, and later, deterministic tiebreakers. Other platforms differ, and EEVPEN adds route type-specific considerations. Multipath is another configured decision, not a contradiction of best path. Use a mnemonic only as a memory aid. For an incident report, show the candidate paths, the actual attribute values, and the platform's stated selection reason. BGP selection produces a route whose next hop is another address to resolve. The router recursively looks up that address in the routing information base, often using an IGP route to a loopback. That recursive result supplies an outgoing interface and an adjacency, which can then become forwarding information in software and hardware. If the next hop is unreachable, the BGP candidate may be invalid or may fail to install even though the neighbor remains established. This is the bridge between control plane and data plane. In an EEVP and fabric, a remote VTEP address carried as a next hop depends on the routed underlay. Prove the selected BGP path, the recursive route, the adjacency, and the installed fib entry separately. IBGP carries externally learned and locally originated BGP reachability across one autonomous system without adding the local autonomous system number to AES's path. That preserves the interdomain path, while internal policy uses local preference and other controls to choose exits consistently. IBGP does not replace the IGP. The IGP provides reachability to BGP session endpoints and next hops. IBGP carries policy-rich destinations that should not burden the underlay. A common design is therefore layered. The IGP knows infrastructure addresses and loopbacks, while IBGP knows external routes or overlay control plane objects. If the IGP loses the selected next hop, the BGP route becomes unusable even though its AES path and local preference remain unchanged. A route learned from one IBGP peer is not advertised to another IBGP peer under the base rules. Because an IBGP advertisement does not prepend a new autonomous system number, a S-path alone cannot detect an internal redistribution loop. The simple prevention rule is not to relay IBGP-learned routes. The consequence is a full mesh. Every ordinary IBGP speaker must receive external reachability directly from every other speaker that may originate it. With EN routers, that means n times n minus 1, divided by 2 sessions. 3 routers need 3 sessions. 100 need 4,950. Route reflection and confederations are scaling mechanisms that modify this distribution model while adding their own design constraints. When an edge router learns a route through eBGP and advertises it through iBGP, the external next hop may remain unchanged. Internal routers might know the BGP prefix, but have no route or adjacency for that external address. The route then fails the recursion test. Next hop self makes the advertising internal router become the next hop, usually using a reachable loopback. That is often the right boundary between an external link and the internal routing domain, but it is not a universal reflex. Preserve the original next hop where shared media, root server behavior, or overlay semantics require it. The proof is always the same. Inspect the received next hop, resolve it through the intended IGP table, and confirm the resulting adjacency and egress. A route reflector allows selected IBGP routes to be advertised beyond the base IBGP re-advertisement rule. Clients do not need sessions to every other client. They peer with one or more reflectors. A reflector may advertise a route learned from a client to other clients and to non-clients. A route learned from a non-client may be reflected to clients, while non-clients retain ordinary full mesh expectations among themselves. Originator ID and cluster list help prevent reflection loops. This reduces session count dramatically, but the reflector is now part of the control plane topology and failure domain. Use redundant reflectors, deliberate client placement, stable identifiers, and identical policy. Then verify the path set visible to each client, rather than counting only sessions. A reflector normally selects a best path before advertising it. If the reflector sees paths A and B, but selects only A client may never learn B, even when that client would have preferred B because its IGP cost or local topology differs. This is route reflector path hiding. Poor reflector placement can also create persistent oscillation or suboptimal exit choice when policy and topology do not align. Redundant reflectors improve availability, but two reflectors with the same limited visibility do not automatically restore path diversity. AdPath can advertise additional paths where supported, but it changes scale and interoperability requirements. The design discipline is to align reflection topology with policy, diversify visibility, and inspect what each client actually receives and selects. Multi-protocol BGP lets one BGP session carry more than base IP version 4 unicast, an address family identifier, and subsequent address family identifier name the kind of reachability. During Open, peers advertise the AFI and SAFI pairs they support. Update messages, then use MP reach NL RI to advertise reachable destinations together with a next hop, and MP unreach NL RI to withdraw them. The familiar BGP attributes and policy machinery still apply, but the NLRI has a family-specific structure. This separation matters operationally. The TCP session may be established while IP version 6, VPN, or EVPN is inactive. Prove the base session. Negotiated AFI and SAFI received family-specific routes, selected paths, and forwarding consequences as separate layers. EEVPEN uses EMP-BGP to advertise overlay control plane objects. Route targets control VPEN import and export. EEVPEN route types describe information such as MAC and IP reachability, inclusive multicast membership, Ethernet segments, and IP prefixes. In a VXLAN fabric, the BGP next hop commonly identifies a remote VTEP, while the underlay routes only the outer IP packet to that VTEP. This creates three distinct proofs. The EEVP on route exists and passes policy. The VTEP next hop resolves through the underlay, and Linux or the AISIC installs the required bridge, tunnel, or routing state. BGP does not carry the tenant packet. It carries the structured claim that helps each edge build the overlay forwarding state. A BGP community is a label attached to a route so policy can act on intent without repeatedly matching raw prefixes or autonomous system paths. Standard communities include well-known values such as no export. Extended communities add typed values and are fundamental to VP on route targets. Large communities provide 3-4 octet fields and avoid ambiguity with 4-byte autonomous system numbers. Operators also define relationship labels such as customer, peer, or backup, and provider-specific communities for traffic engineering. The label has no inherent action, except where a documented policy interprets it. Safe use, therefore, needs a namespace, an owner, allowed ingress sources, an action, propagation rules, and sanitization at trust boundaries. A community without that contract is merely metadata that future policy may misread. RFC 8212 changes the safe expectation for external route exchange. Without an explicit import policy, received eBGP routes are ineligible for selection. Without an explicit export policy, no routes are placed in the external ADJ ribout. This avoids the historic failure mode, where a newly established neighbor unexpectedly exchanges everything permitted by broad defaults. If a routing exposes this behavior through BGP requires policy. Its traditional defaults enable the requirement, while a data center profile may differ. So inspect the running platform. Explicit policy does not mean an empty decorative route map. It means permitted prefixes, lengths, relationships, attributes, and route counts are deliberate. Test positive and negative cases. The required route passes, and forbidden routes do not. BGP security is defense in depth. At the transport layer, use authentication where operationally supportable, infrastructure ACLs, and the generalized TTL security mechanism for directly connected external peers. At the peer contract, verify addresses, autonomous system numbers, negotiated families, and expected roles. At the route layer, apply prefix and length filters, autonomous system path checks, maximum prefix limits, next hop policy, and community sanitization. Our PKI route origin validation adds evidence about whether an autonomous system is authorized to originate a prefix. Local policy still decides how to use valid, invalid, or not found states. Monitoring must catch session churn, unexpected growth, rejected updates, and policy changes. Security is not one password on TCP. It is a bounded, observable routing contract. Several features are described as making BGP faster, but they act on different failure windows. BFD detects a failed forwarding path quickly and can drive the BGP session down. It does not prove that a healthy session carries the correct route. Graceful restart can retain stale forwarding state, while a control plane restarts. It reduces disruption only when the forwarding plane remains valid and peers implement the contract correctly. Route refresh asks a peer to reapply policy without resetting the session. It is not failure detection. Fast external failover reacts to interface state for directly connected peers. Aggressive timers can improve detection but also amplify churn. Select each mechanism for a named failure, measure reconvergence, and verify for both stale forwarding and premature withdrawal. Use an evidence ladder. First, inspect the neighbor summary and detailed state, endpoints, autonomous system numbers, timers, capabilities, and resets. Second, inspect routes received from the peer and policy counters to prove the input. Third, inspect the selected BGP route and its stated best path reason. Fourth, inspect what is advertised to the next peer. Fifth, resolve the next hop in the RIB and confirm the FIB or hardware entry. Finally, capture or test the expected packet and a forbidden negative case. In EFRR routing, useful starting points include show BGP summary, show BGP neighbors, address family specific show BGP, received routes or advertised routes where available, show route map, and show IP route. Save exact commands and timestamps. Let us close the chain. BGP peers form a negotiated session over reachable TCP endpoints. Update messages change candidate routes. Import policy decides what is eligible. Attributes express path and local intent. Selection chooses a path whose next hop must resolve. IBGP distributes that decision internally. Route reflection scales visibility with design consequences. MPBGP types the reachability so EVPN can advertise overlay objects. Explicit policy and layered protections bound what enters and leaves. None of those statements alone proves packet delivery. The practitioner habit is to peer deliberately, filter explicitly, select by documented policy, resolve the next hop, scale path visibility carefully, and then prove forwarding. Next, study MPBGP policy and EVP and route types with this BGP foundation intact.